This evening we're going to discuss problem solving. As noted in the knowledge economy lecture, the force impacting organizations has never been more powerful or complex than it is today. Problem solving was always an essential skill, but has become even more important in the knowledge economy. Collaboration helps with problem solving. It's critical that virtual problem solvers know how to define the core problem accurately, develop and understand a variety of options rather than settle on a quick single solution. Problem solving involves all the collaboration technologies. As ideas come to people, they must be able to record them quickly and communicate with the group. This will involve both asynchronous and synchronous communications: chat, email, discussion forums, teleconferencing, video conferencing, web conferencing. We've reviewed these technologies at length, so tonight I would like to focus on problem-solving approaches. Several prominent thinkers have published work on problem solving, and we will look at several of them tonight: Carl Weick, George Polya, and Herbert Krovitz. Polya in particular was interested in problem solving and attempted to reintroduce the discipline of heuristics with his work on modern heuristics. Heuristics had been a field of study in the early Renaissance, and Leibniz and Descartes were practitioners. Problem solving is transforming a problem description into a solution. You start by describing the problem, identify the problem domain, and obtain knowledge about the problem from the knowledge domain, from the problem domain. One strategy is to solve specific cases and then generalize to various groups of cases. An algorithm is a step-by-step solution to a problem. That is the goal of problem solving, is you want to have an algorithm that other people can follow so that they don't have to go through the same arduous work that you did when you solved the problem. Reuse in future is the purpose of the algorithm, so others don't have to rethink the problem solution. Others can reuse the algorithm without needing to understand the principles used in solving the problem. There's many varieties of problem-solving approach. You've probably encountered one or more of these: systems analysis for business, scientific method for science and engineering, software development methodology for programming. Studying a problem-solving approach also helps us learn how to organize a solution to a type of problem. It's not necessarily a repeatable process for success. They're more a set of useful guidelines for organizing a solution. For example, although we have a scientific method, we still haven't come up with a cure for cancer. It's an approach that we organize our studies on cancer to see how we might best solve the problem, but it's not guaranteed to result in a solution. Let's do an overview of the scientific method. We first identify the problem. We review existing knowledge. We formulate a proposition or solution. We design an experiment, which is gathering pertinent information. And in physical sciences, that can be a laboratory type experiment that might directly establish some sort of cause and effect in our model. In social sciences, it might be repeatable case studies or quantitative methods, or even historical information pertaining to the problem. We would analyze the data for relationships and draw conclusions. And then finally, we would ask if the findings can be generalized. The software development method is another approach we could take, and the steps in that are to specify the problem, analyze the problem, design the algorithm to solve the problem, implement the algorithm, test and verify the completed program, and maintain and update the program. Tonight we're going to look at a more general approach to problem solving that was reintroduced by the mathematician George Polya, who created the theory of directed graphs that's used widely in computer science and many other branches of science today. The problem-solving approach is a modernization of what Descartes and Leibniz used in their problem-solving. Design is the essence of man-made sciences, be it engineering, management, or medicine. Design presumes an ability to alter a system and the ability to select the set of operations or steps to accomplish the construction or alteration of the system. In design, you list all the operational steps to solve the problem, and you verify that the algorithm of steps actually does solve the problem as intended. The general high-level steps are get the givens, or the inputs or the data, perform operations to analyze and synthesize that input data into the desired result, and then display the result. Now we'll review George Polya's approach, but before we start, consider this pattern of numbers. It's any 6-digit number where the first 3 digits are the same as the last 3 digits. And just as an example, 920,920, 134,134, 567,567. These are examples of that pattern of number. Well, any 6-digit number of this type is evenly divisible by 77. So the problem we want to solve is, why is that the case? Why is that true? And we'll come back to resolve this problem during the lecture. It's foolish to answer a question or start solving a problem if you don't understand the question or problem to begin with. You end up working for an end that is not desired. A verbal statement of the problem is a good starting point. Polya recommends stating the 3 aspects of the problem. And for Polya, the 3 aspects are: 1, what is known? In other words, what is the data, or what are the givens? Secondly, what is unknown or required? This is the goal. Find the unknown or reach the requirement, satisfy the requirement. And then the third aspect of a problem are the conditions. And these are the relations and potential relations between the known and unknown. We start with general domains of knowledge that may relate knowns to unknowns. And within these domains, we keep searching more specific paradigms until we get a set of relations to try and to test. So in addition to the 3 aspects of the problem, we also want to look at the 4 problem-solving phases that Polya defines. In order to group conveniently the questions we will ask during problem-solving, Polya distinguishes 4 phases to problem-solving. First, we have to understand the problem to see clearly what is required. Second, we must clearly see how the various items in a problem are connected to devise a plan to link the unknown to the givens. And third, we carry out the plan. The worst may happen if someone starts out on computations or constructions without understanding the elements of the problem and how they're connected. So this is the third step. And then fourth, we look back on our plan and the results. We review and discuss those to see if there's any way we can improve our approach. These phases are not strictly sequential, and the whole process involves some trial and error. So phase one, let's start our review here with phase one of problem solving, understand the problem. First, we want to understand the problem as a whole, and then as the three parts of known, unknown, and conditions. We want to use future perfect tense when thinking about the problem. Future perfect tense is starting with the end in mind. The Romans called this res base finum, and studies show that a future perfect tense rather than simple future tense is more conducive to creativity. Simple future thinking is starting in the present and working to the future. Future perfect tense starts in the future, assuming the event occurred, and then works backward to the present. The simple future approach is difficult because any possible outcome is considered in our thinking, including those not on the path to the desired result. In future perfect tense, in contrast, it's assumed that the action in the future has already occurred, and the narrative predictive application is how we actually accomplish that. So there's some aphorisms that go along with phase one from Polya. He says, a wise man begins at the end, a fool ends at the beginning, and a fool looks to the beginning, the wise man regards the end. With phase two, now let's plan the problem solution. We have to allocate time for problem solving. We have to understand the impact of the problem solving that we'll have on the global virtual team processes, on our communications, on the cultural styles, on the leadership approach. Understand the learning that is necessary for us to solve the problem. Understand the impact on the mission. We want to relate the problems, the knowns, unknowns, and conditions to the mission. Support of the mission is the motivation to solve the problem in the first place. A plan for access to knowledge domains and experts in those domains. And these plans that we're preparing for problem solving are general outlines, and as more data is discovered, it will be added to the outlines we're preparing. So we want to execute the plan. We have to train our people as needed. We have to revise our communication and leadership approach as needed. Search knowledge domains for relationships to try reaching unknowns from knowns. Adapt plans as necessary, and the plan must be adaptable. And Polya notes that insects keep trying the same approach to overcome an obstacle. They never vary their plan. And in contrast, mice will vary their plan and try different approaches. Vary the problem definition to adapt the plan to our particular circumstance. We might change the knowns, add more knowns, remove some that are irrelevant and might lead us down rabbit holes. Change the relationship set. Search other knowledge domains than those having an immediately obvious connection to the knowns and unknowns, and look at the different aspects of the unknown. And Polya has an aphorism for this, and that is, a wise man changes his mind, a fool never does. Phase 4. We want to re-examine the solution, look for alternative solutions. More solutions is better than one solution. As more information is discovered, or because of a changing situation, one of the solutions may be invalidated. So it's better to have more, and we should look for alternatives. Then we also want to consider, can we generalize the solution so it can be applied to groups of similar problems? The approach is to start with a specific example to understand how to apply the conditions or relations that we learn about to the knowns and derive the unknowns from the knowns and the relationships. And then once a specific example is solved, we want to generalize the algorithm to help people in other problem domains where this might be a relevant model to apply. Now we'll do a simple example of problem solving. Let's say Bob wants to buy a square-shaped piece of property that is 100 feet on each side. In addition, the property must be level with two sides of the square running exactly north-south and the other two sides running exactly east-west. The question is, can Bob buy such a property in the United States? So, respice finum, we start with the end in mind. We want a square piece of property in the U.S. with sides running exactly north, south, or east-west. So real estate transfer is governed by U.S. legal code, and our general search domains will be squares, latitude, and longitude, and U.S. real estate law. The nature of a square from our search of this knowledge domain is it has four sides of equal length and opposite sides are parallel. And then we also search the knowledge domain of longitude and latitude, and we find that latitude lines run north-south and they converge to a point, either the North Pole or the South Pole. So latitude lines are not parallel. So we found an answer to our simple problem. No, Bob cannot buy a square piece of property in the U.S. with 100 feet on each side and two sides running exactly north-south. Exactly, and north-south lines do not run in parallel. As another example of simple problem solving, let's say that Mama has just filled the cookie jar when 3 children went to bed. That night, one child woke, ate half the cookies, and went back to bed. Later, the second child woke, ate half the remaining cookies, and went back to bed. And still later, the third child woke up, ate half the remaining cookies, leaving 5 in the jar. How many cookies were in the jar to begin with? So we'll solve the specific problem to understand the steps involved. And we had 5 cookies after the third child had finished eating their share. So that's half of the cookies that were there when the third child woke up. So when the third child woke up, there was 5 times 2 or 10 cookies. Likewise, when the second child woke up, there was 10 times 2 or 20 cookies. And when the first child woke up, there was 40 cookies, and that was the original number of cookies. A generic algorithm for this problem will work with any number of remaining cookies and work with any number of children. That might be one way we can generalize it so that other people can apply it to similar type problems. So to generalize this cookie heist algorithm, we get the number of children, we get the number of cookies remaining, we don't use them as fixed, and we have an algorithm that while there are still children that have not raided the cookie jar, we multiply the number of cookies by 2 and reduce the number of children by 1, and when we finally get all the children have been accounted for, we display the original number of cookies. Not all problems are as simple as the previous two, and here are some general approaches to take when solving complex problems. Weick and Polya give numerous techniques to solve difficult problems. The next few slides, including this one, are a sampling of those approaches. First is work the problem backwards from output to input. This approach was first formalized by Pappus, a 3rd century Greek mathematician. Instead of starting with the givens and working towards the requirements, he suggested doing the opposite. We start with what is required and take it for granted, and then look at what the causes of those requirements might be, those required functions or features, and then what the causes of those causes might be, iterating until we can associate a cause with some of our givens. Psychology provides research backing up the effectiveness of this approach, and it is in essence thinking in future perfect tense again instead of simple future tense. We might want to use analogy. Analogy is a sort of similarity. Similar objects agree with each other in some respect. Analogy pervades our thinking from everyday conversation to our highest forms of art. So using an analogy strategy for problem solving, we search for problems related to our problem and then adapt the solutions we find to our problem and see if they work. This is an iterative process. Failures should give better refinement of the problem and its analogous characteristics. In solving a proposed problem, we can often use an analogous, simpler problem in our solution, either the method or the result. We may want to change the analogous solution if it doesn't work and try various forms of the solution until we find one that does work. An historical example of using analogy is from science. The logic to determine the center of gravity of a tetrahedron proved difficult. The problem was solved by Galileo, and he solved it by looking at a simpler problem. Find the center of gravity for a triangle. A tetrahedron is a three-dimensional triangular figure. Then he adapted the solution of the simpler center of gravity for a triangle to the more complex proposed problem. According to Polya, it sometimes takes a little sagacity to hit upon the idea that solves the problem. Krovitz noted that we only use 10% of our brain in our conscious thinking. The other 90% is our unconscious. And he reported that Bertrand Russell solved problems by digesting relevant information and then doing something else. After he had stayed away from the problem for a while, he came up with the solution quite often. And my friend at work, Kenan Chinnasamy, says he works in the same manner. So although Polya calls sagacity enlightened guessing, it's possible that it's really the unconscious mind at work. Yet another approach is a stepwise refinement. Here we separate the problem into its constituent parts and start decomposing each of those with stepwise refinement. The knowns, the conditions, the unknowns. Top-down design, we list major steps and break the problem into parts. Then break the parts into parts until each of the parts is easy to solve. Breaking the problem into parts helps us clarify what needs to be done. And at each stage of refinement, the new parts become less complicated and therefore are easier to understand. Parts of the solution may turn out to be reusable. Breaking the problem into parts also allows different experts to work on the solution. Induction is the process of discovering general laws by observation and combination of particular instances. Induction tries to find a regularity and coherence behind a set of observations. Its most conspicuous techniques are generalization and analogy. Tentative generalization is based on analogy. In other words, we set up a model that we say is analogous to the situation we want to study, and then we run experiments in that model in a controlled setting, and we look for patterns that we can derive generalizations from. So induction is the basis, really, of scientific research. Heuristic means serving to discover, and it had been a branch of academic study to learn the rules of discovery and invention back in the early Renaissance. And it was Leibniz and Descartes were leaders in this school of study. In heuristics, reasoning is not as formal as it is in science or engineering, where they strictly apply rules. In contrast, the goal of heuristic reasoning is not a formal proof, but the generation of plausible solutions. The idea is generating provisional solutions, and only one of these meets certain tests is formal rigor applied to its construction. Heuristics are often based on induction or metaphor, of course, just like the scientific methodology. An essential aspect of heuristic approach to problem solving is the variation of the problem. Restating the problem, restating the givens, restating the unknowns. There is also decomposition and recombination, as well as induction. So let's look at our problem about the number 77. We might restate the problem from why these numbers are evenly divisible by 77 to how they are formed to produce that pattern. So iteratively, we might also ask a further question: what is the pattern anyways that we're looking at? And the answer to this question is something we can answer. We have a 3-digit number and repeat those 3 digits to the left. So 3 digits is the core of the pattern. The pattern is that these 3 digits repeat in a 6-digit number. So what does that mean? What does the 3-digit number mean? What does the 6-digit number mean? Well, the 3-digit number is hundreds, 0 to 999. And the 6-digit number is hundreds of thousands. So how do we create a 100,000 number from a hundreds number? Well, we'd multiply it by 1,000. And then we'd get the same 3-digit number, but it'd be followed by 3 zeros. Not what we want. So how do we get the repeating 3-digit numbers? Well, we take the 3-digit number, like 327, and we multiply that by 1,001 to get 327,327. So each of these numbers in our pattern is a multiple of 1,001. In other words, any 6-digit number where the first 3 digits are the same as the last 3 digits is evenly divisible by 1,001. And 1,001 is evenly divisible by 77, and so that gives us our answer as to why that pattern of numbers, where it's a 6-digit number and the first 3 and the last 3 digits are the same, why that pattern of numbers is evenly divisible by 77. We now know we have an answer why that's the case. And we did it by heuristic reasonings, restating the problem, restating the givens, restating the relationships. Appendantry and mastery. These are two opposite attitudes towards rules. Appendantry is the rigid application of a rule, and mastery is the application of a rule with a natural ease, with judgment on the proper timing, and in cases where it should apply. The realization is that rules are learned in trial and error, success and failure, and by experience in applying them. So We should ask no question really or make no suggestions indiscriminately based on rules. We have to be open-minded and consider the situation and the context that we're dealing with. Reductio ad absurdum is the association of an assumption with an obvious absurdity to demonstrate it is false. Satire likewise does for drama what reduction does for logic. It adopts a certain opinion and stresses and overstresses it until it leads to an absurdity. Apollyon noted again that insects keep trying to escape through a window pane, but they keep trying to go through the same window pane, and they do not try to go to another window that might be open. A mouse acts differently. The mouse will vary its tries until it makes an escape. So try again is a current popular song today and popular advice, but it may be better to instead try different. Success in solving a problem is a result of organizing and mobilizing knowledge about the problem. Weick advises thinking, and this means that a team should attempt to use verbs rather than nouns. Verbs anticipate objects and events and apply meaning to them more so than nouns. Verbs capture process better than nouns. Nouns preserve spatial snapshots, and verbs capture processes, motion, change, flow, temporal aspects of a situation. So verbs are better really at analyzing a problem than nouns. That's why Weick advises thinking. Mutate metaphors. Metaphors are figures of speech that transform a term from what it ordinarily designates to one of interest. It can aid in communication, and it really is a platform for embellishment to aid in connecting with other ideas. Think about the problem, and it helps us think about the problem in a different light, from a different perspective, and consider different associations with the problem. For example, we could say that he dived into the water like a warrior instead of he dived into the water bravely, because warrior has more connotation. It's a metaphor, and we can embellish on that a lot more than we can just a plain old adverb bravely. Organizing is important to problem solving also. The enactment function is interaction with the environment to gather input and to deliver results. Just as an example, an input for a project team would be customer needs, and a deliverable might be an approved requirements document. Several iterations of eliciting requirements and reviewing a draft requirements document might take place, but eventually we're going to get the final set of inputs from the environment and deliver our output to the environment. And this is all enactment. The second organizing function, selection, is the application of appropriate models to manage the organization of work. So let's continue with the project management as an example. In project management, selection would encompass the 5 process areas. An example of the type of decision made in selection, should the project use an earned value management process to monitor performance? And finally, retention is the storage of knowledge. So we know how to do things and we remember how to do them. This is the repository for the knowledge of the processes, values, and standards applied to the organizing. And of course, in project management, it would be the knowledge areas or the PMBOK. The internet could be considered a retained knowledge repository. If none of the retained knowledge is relevant or a good fit for the issue the team must resolve, then it must develop new knowledge, in other words, new approaches to solving the particular issue. So here's a graphic of enactment, interaction with the environment. It obtains situational awareness, and it executes our processes on the environment. A selection, it identifies the characteristics of the situation and then searches retained knowledge for matches. And you don't always get a good match, in which case you have to then do the skillful work of defining a new algorithm. And then retained knowledge are algorithms that have worked in the past, problem-solving methodologies. So algorithms, the study of algorithms began as a subject in mathematics. The search for algorithms was a significant activity of early mathematicians. The goal is to find a single set of instructions that can be used to solve any problem of a particular type. In other words, a general solution. The expectation of algorithms are that once a successful algorithm is developed for a situation, we don't need to understand the principles that went into the solution. The intelligence is encoded into the algorithm. The task is reduced to following the instructions. More highly skilled people are used to solve the problem. Less highly skilled people can execute the algorithm for the solution. Okay, a definition of an algorithm is it's a step-by-step solution to a problem, and it has a finite set of executable instructions that directs a terminating activity. So let's look at two examples of algorithms. A classic one is finding the greatest common divisor using Euclid's algorithm. Euclid was one of the early mathematicians that was very interested in developing algorithms. And then we'll look at one that's fairly ambiguous, and we can contrast that with a good algorithm. Okay, so Euclid's algorithm is we want to find the largest positive integer that divides evenly into two positive integers that are given to us as input. In other words, the greatest common divisor. So the algorithm is let m and n be two positive integers where m is greater than n, divide n by n, and call the remainder r, so we're getting the modulus. If r is not 0, then m equals n. In other words, the smaller number becomes the larger number, and we discard the larger number. And n becomes the remainder number. And we keep looping through step 2 and 3 until we finally get a remainder of 0. And once we have the remainder of 0, n is our greatest common denominator. So here's an example, the greatest common denominator of 24 and 9. We divide 9 into 24, we get a remainder of 6. That's not 0, so we keep going. We move 9 over to m, and we move 6 over to n. Divide n into m, 6 into 9, and we get a remainder of 3. Again, it's not 0, so we're not done. We now move 6 to m and 3 to n. Divide 3 into 6, we get 0 as the remainder, so we're done. So 3 is the greatest common denominator of 24 and 9. So do we need to know the theory that Euclid used to come up with this algorithm in order to use it? No. All we really have to know is the steps. And it doesn't really take a lot of domain knowledge or intelligence to apply the algorithm. It does to develop the algorithm, but not to apply it. Here's an example of an ambiguous algorithm. Washing hair instructions. First, you lather. Second, you rinse. Third, you repeat. And these instructions can be hard to follow because there's no terminating condition. We just keep doing this algorithm. And that's known as an infinite loop, and we definitely don't want to get caught in those. So the idea behind algorithms is once an algorithm has been discovered, we don't need to understand the principles that went into it. The intelligence is encoded into the algorithm. The task is reduced to following the instructions. Just as another example, let's look at how we might go about decoding this sentence. This is a Vigneri's cipher, and it was once notorious for being a tough code to break, but now most systems can do it with fairly easy facility. Basically, in this particular case, we just add 4 positions to each letter. So P becomes R1, F, or Q1, R2, S3, T is the 4th position from it. D becomes E, F, G, H, and E becomes F, G, H, I, and so on. And what we get as the deciphering of the sentence is this is the correct answer, just adding 4 to all of the letters. For example, the N's, you add 4 positions to the N and you get O, P, Q, R. So we have 2 R's. Adding 4 to Y, we get Z, A, B, C. And 4 to K, we get L, M, N, O. So C-O-R-R-E-C-T for correct. So just in summary, there's 2 steps to algorithms. First, we have to discover the underlying algorithm, and that involves problem solving. And second, we represent the algorithm in a tool that mechanically or automatically transforms inputs, givens, or data into desired results. Algorithm discovery is the more challenging of the 2 steps, and it requires problem solving. Problem solving is pertinent to all fields of study. Many methodologies have been proposed, but you can't reduce it to an algorithm or a repeatable process that always leads to success. It's more a set of useful guidelines. And that's it. Thank you.